Today we're taking a look at indeterminate differences. This is a situation where we're doing infinity minus infinity. It doesn't necessarily equal something that we can actually know. It's not like infinity minus infinity is 0 every time, or infinity minus infinity is going to be infinity every time. We're going to get some different results depending on the actual functions involved. And so start by writing this down to your notes, and then we're going to see how we can actually deal with solving these sorts of limits. As you take a look at these two lines here, notice that they basically are saying the same thing. It's just saying the same limit where we're doing two functions that are subtracting. If that gives us infinity minus infinity or negative infinity plus infinity, in other words, it doesn't matter which one's negative or positive, but if we end up getting a positive and a negative infinity out of those two, then we have what's called this indeterminate difference. And you'll notice the hint down here at the bottom. In order to deal with these, we're going to try to turn the difference into a fraction, because if I can take my indeterminate difference and write it as a fraction, then I actually have a rule that we can use to deal with it. We have L'Hopital's rule. And so we'll be able to use L'Hopital with actually solving that and finding that limit. And so to start with then, I want to just start by turning a difference into a quotient. That is, I'm going to try to write this subtraction as a single fraction. Now the first thing in actually turning these into a single fraction is writing each of these as a fraction. Going back to our definitions of some of these trig functions, cosecant, remember, is 1 over sine. So this is going to be 1 over sine of x, minus, and then cotangent. Cotangent is cosine over sine. Well, this one works out very nicely, though, doesn't it? Because in order to subtract them, we need a common denominator, and here we already have a common denominator. And so I can go ahead and do the subtraction on the top. It becomes 1 minus the cosine of x, all over sine of x. So there we've written it as a single quotient. By doing that sort of a move, it allows us to find limits that we might not be able to find otherwise by using L'Hopital's rule. In fact, I'd even like to see that with this. So let's actually find this particular limit. Notice it's the same stuff inside the parentheses, just now we're going to find the limit as x approaches 0 from the right side. All right, and so step 1 of evaluating this limit is to do what we just did, and that is to turn it into that fraction. Because, and I suppose I should actually go back and mention why. Notice if I took the 0 and plugged it in for x in both of those, I get infinity minus infinity. So it is in fact telling us that we have to end up doing that fraction move. All right, so remember that gave us 1 minus cosine of x over sine of x. And now that I've written it as a fraction, I can now use L'Hopital's rule to find out what this limit is. So that rule, of course, tells us find the derivative of the top and the derivative of the bottom. So go ahead and do that. So I'm taking that derivative on the top. Of course, the derivative of 1 is 0, so that goes away. So that's the derivative of negative cosine of x, and derivative of cosine is negative sine. So it's like the top is a negative sine. So we'll just call that sine of x. Oops. And then on the bottom we do the derivative of sine, which is just cosine of x. All right, we took the derivative of top and bottom. Now I want to try plugging in that 0 and see if it's actually going to give me something useful. So the next step, we are going to do sine of 0 over cosine of 0, and we're hoping that this does not give us another 0 over 0. Let's actually see what that gives us. What is sine of 0?
0.
That is 0. Okay, it's 0 over, what's cosine of 0? 1. At least it's not 0 over 0. So that means it's actually giving us a value. So 0 over 1 equals 0. And so that then is our final answer. We know then that the limit of this function as x approaches 0 from the right-hand side, is 0. Now this problem is an example of the type that you will typically do and is most commonly approached for being able to do these indeterminate differences. But there are some other scenarios that can crop up, and I want to show you one of those here. So go ahead and write down this problem. And let's take a look and see what happens if I just plug in the infinity at the start. If I plug infinity into x squared, infinity squared is just infinity, minus infinity then. And so notice it's that indeterminate difference, because I'm trying to do infinity minus infinity. Okay, so the next step. Well, there's not really a nice way in this particular problem to turn it into a fraction. It doesn't lend itself naturally to that. But what it does lend itself naturally to is factoring. Because you notice I have an x in both terms. So let's factor out an x there. So if I do that, that's going to give me x times x minus 1. Technically speaking, all of this is still just one big term there. But you'll notice what that did for us? Let's try plugging in the infinity now. If I now plug in infinity for x, okay, so that would become infinity times, and we want to plug in infinity there as well, infinity minus 1. Well, infinity minus 1 equals infinity. And so we're really doing infinity times infinity, but that we can do. It's no longer like infinity minus infinity. It didn't give us infinity times 0, which would also be indeterminate. It gave us infinity times infinity, which we know is infinity. And so we didn't even need to use one of those different techniques or anything like that. In this case, we could actually just manipulate the equation to look a little different and then plug in our infinity, and we actually got a result out. So this one's actually approaching infinity as x is approaching infinity.